Hi, everybody. Welcome to section 3.2, where we're going to be talking about the second derivative and the behavior of the function. So, here our learning objectives for this section is going to be we're going to learn how to find hypercritical values. We're going to determine the intervals of concavity based on the second derivative. We're going to describe the behavior of a function using the first and second derivatives together. And we're going to use a second derivative test for local extrema. What this means is, max or min. Okay, so in last section, right, in 3.1, we learned that the intervals of decrease are found by looking at the first derivative, right? Our next topic is about the function's concavity, which is about the second derivative. So concavity and points of inflection, here's a definition box that if the graph of f lies above all of its tangents on an interval I, then f is concave up on the interval I. And likewise, if the graph of f lies below all of its tangents on an interval I, then f is concave down on I. So if that definition is a little too much, what it's really saying is that this right here is just concave up. It's concave up. You can think about it as like a U, an upside down bell. But if it's pointing up, it's concave up. And likewise, if it's down, if it's upside down U or the shape of a bell, this one is concave down. Okay, so that's just what the graphical representations of them are. So how do we actually test for concavity? Well, suppose that the second derivative exists on an interval. If the second derivative is greater than zero, then it is concave up on I on the interval. And if the second derivative is less than zero, then it is concave down on the interval. So think about it like increase, decrease, right? What we just covered. So if it's positive, then it's going up. If it's negative, then it's going down. Okay. So another definition here is an inflection point, and this is just where concavity changes. Where you're changing from concave up to concave down, or vice versa, concave up to concave up. There's usually a point where this change happens. So it says, so which of the below points are inflection points? This is referring to on the next page of this example right here. So which are the inflection points? So I'll say, what are the inflection points? Okay, and remember, this is just where concavity changes. All right, so we're just looking through these and seeing where the concavity is changing. So I'm following along, right? And I notice right here at C, I switch from concave down to concave up, right? It's going down, but now it's flipping up. So right here at C, it's an inflection point. Goes from concave down to concave up. Okay, so that's one inflection point. Now let's keep going. We're still concave up, and then boom, right at E. Sorry, not at E. We're concave up, and then boom, right at D, we switch from concave up to concave down. Right? You see the switch right there. So here at D, goes from concave up to concave down. All right, let's keep going, following along, and then we're still down, and then boom, right here at F, we switch to concave up, right? we're making that switch right there. So same thing goes from down to concave up. Let me just copy this right here. Okay. At F. Okay, so if we go through these lists of numbers, right, we're talking about the points on here, A, B, C, D, E, F, G. We're just referring to these ones right here, right? So are these points of inflection? Here you would say no, no, yes, yes, no, yes, and no. Because at C we have a point of inflection, at D we have a point of inflection, and at F we have a point of inflection. So C, D, and F. Okay, so that is us checking it out graphically, right? But what if we actually don't have a graph? So there's actually a way to check these out. So I'm gonna come back to the second derivative test, but what you would need to do, much like increase, decrease, right? You would need to find something called a hypercritical value. And that's when the second derivative equals zero. Okay, so you would find the second derivative, set it equal to zero, and find the hypercritical value, which we'll see in the example. But before we get to that, just want to cover a new kind of tool we have, so which is a second derivative test. So if if you have your critical value, right? And if you plug that critical value into your second derivative, then and it's greater than zero, then you have a local minimum. And if you take that critical value, put it in the second derivative, and it's negative, then you have a local maximum. Okay, so that is the second derivative test. So this is about still max and min, right? We're not talking about concavity, we're talking about max and minimum. It relates to the concavity with a positive and negative second derivative, but we're still talking about that max or min with the second derivative test and our critical values. So critical, I'll say like C is critical value. Okay, so a little refresher from 3.1. Okay, so let's go ahead and check out this example here. So given the function f of x equals 4x cubed plus 3x squared minus 6x plus 1, his first question here is asking us, find the hypercritical values. So what we really need to do is just find the second derivative, set it equal to 0, and solve. So what I'll say here is get second derivative. Okay, so we have f of x equals 4x cubed plus 3x squared minus 6x plus 1. And the first derivative of this is going to be 12x squared plus 6x minus 6. And then I want to find the second derivative though. So the second derivative of this is going to be 24x plus 6. All right, so once again, it's when the derivative equals 0. So I got to set this equal to 0. So say set the second derivative equal to 0. So I'll have 24x plus 6 equals 0. I'm going to subtract 6 to both sides. I'll get 24x equals negative 6. I'm going to divide both sides by 24. I'll get x equals -6 over 24. So then x, if you reduce -6 over 24, you get -1/4. Okay, so x equals -1/4 is a hypercritical value. Okay, so we only have one. We have one hypercritical value. But okay, so next question is find the intervals of concavity and the inflection points. Okay, so let's go ahead and focus on the first one, intervals of concavity. So much like with increase, decrease, this is where we need to draw a number line, plug in some test points, and figure out if it's negative, positive, and that will tell us if it's concave up, concave down. So let's go ahead and try that out. So I have a number line here. All right, I'm only testing out a couple things, right? My hypercritical value is -1/4, right, from up here. So I'm just going to pick some numbers to the left and right of it that are easy to work with. So what I'm going to pick is something like to the left of it, -1, and I'm going to pick 0 because 0 is just really easy to work with, and also 1 and -1. So, kind of saying what we're doing, number line, right? And I'm going to test out some points with the second derivative. Okay, so I'm going to go out to the side and calculate what these guys are. So we're going to plug it into the second derivative, right? Plugging it into this guy. So this would be f double prime of -1 equals 24 times -1 plus 6, which is just -18, which is negative, which means it's going down. Okay, so right here, down. And then secondly, plugging 0 into that second derivative, 24 times 0 plus 6, which is just 6, which is positive. So it's going up. All right, so we're using this rule right here in the first page, where if it's second derivative greater than 0, concave up, second derivative less than 0, concave down, positive, negative. So we can actually write our concave up and concave down now. So remember, we're not just stuck to these numbers, we're actually going to infinity, right? So we're going to be using negative infinity and infinity in our concave up, concave down statements. So I'll say concave up, right? We're concave up when we're increasing, right? So we're going to be concave up from -1/4 all the way to infinity. So concave up, -1/4 to infinity. All right. So what about concave down? We are concave down when it's decreasing, right? So we're going to be concave down from negative infinity all the way to -1/4 because that's where we are negative, it's going down. So this would be negative infinity to -1/4. Okay, so that is concave up or down. And for inflection point, right? Inflection point is just the actual coordinate point of your hypercritical value. So inflection point, let me highlight this and bring it up here because we're running out of room a bit. But inflection point, right? What we're going to do is just take this hypercritical value and plug it into our function. So what I'll say is inflection point, I'm going to abbreviate it, IP, is when this, sorry, is when the second derivative equals 0, which is negative x equals -1/4. So what we're going to do is just take this -1/4 and plug it into our function to get the coordinate point. So f of -1/4 equals 4. Running over a room a bit, I apologize. Is well, is 4 times -1/4 cubed plus 3 times -1/4 squared minus 6 times -1/4 plus 1. So if you do all these calculations, right, what you end up with is a fraction 21/8 or decimal, right? 21/8 is just 2.625. So really, your inflection point is just -1/4 and 21/8. Okay. So that takes care of part B. So for C, it's asking us to find all relative extrema for the function. So what this actually means is just find the max and min. And within this problem, we're going to be using the second derivative test, right? But first, what we got to do is find our critical value. Don't get confused with your hypercritical value. That's the second derivative. Critical value is your first derivative. First, second. Okay, so we need to find the first thing we got to do is find our critical value. All right, I got to find my critical values. Luckily, I have my first derivative already. So I have f prime of x equals 12x squared plus 6x minus 6. And now I just got to set this equal to 0 and solve for x. So what I'm going to do is create a second page. Okay, so find critical values, and I'm going to set this equal to 0, right? Some 3.1. So 12x squared plus 6x minus 6 equals 0. And we're just going to factor this and solve for x. So luckily they have a common term, so I could take out a 6 from each of these. So I'll take out a 6, and I'll end up with 2x squared plus x minus 1 equals 0. And then you can divide 6 to both sides and get rid of that. So 2x squared plus x minus 1 equals 0. And then the way to factor this is what you would end up with is 2x minus 1 times x plus 1. Okay. So you would solve for both of these. So you move 1 to the right side, right? You would get 2x equals 1. And then you divide 2 to both sides, and you should end up with x equals 1/2. All right, and likewise, you can move -1 to both sides, so you can get x equals -1. So our critical values are x equals 1/2 and x equals -1. All right, so what do we do with these critical values, right? We want to use the second derivative test. We want to use this guy. So what we want to do, we have our critical values, we just found them. We want to plug them into the second derivative and see if we get a positive or negative value. So let's go ahead and do that, because that'll tell us whether it's a max or min. So I'll say like step 2, second derivative test. Excuse me, second derivative test, and then plug x equals 1/2 and x equals -1 into the second derivative, which is 24x plus 6. So let's go ahead and check that out. So f double prime of 1/2 is 24 times 1/2 plus 6, which equals 12 plus 6, which is 18, which is greater than 0, meaning positive. So by the second derivative test, since it's positive, then it's a local minimum, right? 18, so it's positive, so it's a local minimum. So let me make that note. Positive local min. All right, so let's check out -1 now. F double prime of -1 is 24 times -1 plus 6, which is then now -18, which is less than 0, meaning negative. And by that second derivative test, this means it's a local max. So let's put this all together. What this means is the function f of x has a local min at x equals 1/2 and local max at x equals -1 using the second derivative test. Okay, so we have 2 ways to determine if it's a local min or max. One from 3.1 where we use a number line and etc. Or we can just use a second derivative test. Just be careful in the future. It might not be, the second derivative might not be easy to come about. It might not be a regular polynomial like that. So it just depends on what you would want to use. But you have 2 tools to find min or max. But thank you for this video. We'll see you next time. All right, bye.